Alrighty, here we go. So with this proof, we are going to talk about quadratic congruences and their solutions and the existence of solutions. First off, let's just take a quick moment to talk about what a quadratic residue is. So in brief, you can think of it sort of like a remainder. It's when we have an x squared on one side of our congruence, and then we also have some restrictions on what our values of x could be. X has to be less than m, and it's also relatively prime to m. So just again, notice that the value that we would be squaring in a congruence has to be less than what our modular value is, and then also relatively prime. So here's our theorem. We want to suppose that P is an odd prime, and if P does not divide A, then our congruent statement has exactly two solutions or no solutions. So then again, hear that again, we have exactly two solutions or no solutions. Let's begin our proof. Here's our statement again that we have an odd prime, we have P does not divide A, and that we're going to try to show that there is exactly two solutions or no solution at all. Setting our scene, we know that our values need to exist in our integers. We know that P needs to be an odd prime and P does not divide A. We can assume that there is a congruence. We can assume that there is a solution to this congruence, and that's going to be our driving factor here. We're going to do a proof by assumption and then hopefully prove it true. So we can also assume that P minus R would also be a solution, and it would be different from R. I do have a quick note about this so we can kind of take a moment and breathe and we can see why this is true. If R was congruent to P minus R mod P, then you can add R on both sides. We would end up with 2R is congruent to P mod P. We wouldn't generally write it as a residual of P, so we would change it to a 0. So you can see we do result in 2R is congruent to 0 mod P. We know that 2 and P, their GCD is 1. So we would be able to write this as R is congruent to P mod P. So that contradicts our earlier statement, so that's kind of why we want to show that this is going to be different from R. All right, so here we go. This is what we have so far. Let's see what we can add on. So S can be any solution, okay? So we're going to let S be any solution to this congruence. Therefore, R squared would be congruent to S squared mod P. We can use our properties of congruences again. If you add S squared to both sides, subtract S squared to both sides, you get R squared minus S squared, and now it's congruent to 0 modulo P. From here, we can see that this would imply that there's no remainder. This would imply that P divides R squared minus S squared. We can take a moment to factor this difference of squares. R squared minus S squared does become R plus S, R minus S. I always like to think difference of squares, different signs. And from this, we could know that P would divide. We just now have our factored form, R plus S, R minus S. Therefore, this gives us two situations, two cases that we need to talk about. So P would divide R plus S, or P would divide R minus S. Case 1, we'll look at the plus. So it would imply that S is congruent to P minus R mod P. And case 2 would give us that S is congruent to R mod P. From here, you can see that these are really the only two solutions that you would get if there were a solution. So your solutions be included here. These are all least residues of modulo P. So then, therefore, you can see again, there's only two solutions if there are solutions, or if we do not have a solution, it would just be 0, no solutions.